In this lecture, I want to talk or continue to talk about the colors that come with these transition metals that are results of crystal field theory for octahedral complexes. So when we think about the color of something that we're observing, there's a couple ways that this can happen. If all color is absorbed by a compound, it'll look black to us. And if no color is absorbed and it's all reflected, we'll observe it as white. Now, if it is something that actually has a color that we correspond with, something that's like Roy G. Biv, or in our color wheel, other than black and white, what's going to be happening is one of two things. Either all of the light is being absorbed and then just one wavelength or a series of wavelengths are being transmitted. So that would be this example right here. And then we're observing this wavelength of light that's coming off. And so let's say that's yellow, and we would correspond, like a wavelength that corresponds with yellow light. We would observe yellow light. The other way we would observe yellow color in a compound is that it is only absorbing energy at a specific wavelength or a series of wavelengths that when it is absorbed, we see the rest of the colors present itself as yellow. And so this is the type of wavelength absorption that we're seeing with these transition metals compounds. And so here's an example here. So something, we send white light through a sample. And in this sample, it absorbs these orange and red wavelengths here. And it's going to, let's say, absorb that energy to promote electrons into the d orbitals that are unoccupied. Well, the rest of the wavelengths that are not absorbed continue through, but now our light will perceive all of the wavelengths of white light except the orange and the red. And when that happens, we see a blue color. So when it absorbs red, we see the blue. So if we look at, and so this gets to the idea that the observed color that you see is actually the complementary color of the one that's actually absorbed. And so this blue color example here, we are absorbing in this region here, this red-orange region. And so we're going to see the opposite. So we're going to observe the color that's on the opposite of this complementary color wheel. If we were absorbing yellow light, green light, then we would be seeing violet blue instead. And so these kind of go across from each other like that. And so here, here's another example. This is titanium with 6 water molecules covalently coordinated to the titanium. Remember, we're looking at a titanium +3, so we just have one electron to worry about. And so we have our electron or our d orbitals split based on the way the ligands are arranging themselves. We have 6, it's an octahedral pattern, and we have 1 electron. Well, as white light is shined onto that compound, it is going to, here's our white light, excite up to the next energy level. And the energy difference between these d orbitals when they split in these coordinate covalent compounds corresponds to the amount of light that we would be able to observe in the visible spectrum. And so that's why we're seeing these colors that are actually visible to us. So for this titanium complex, which is shown here, like a sample of it, and then we have a UV vis spectrograph here. So this is using UV vis spectrophotometry. I'm spelling it wrong. To see what light is absorbed by the compound. And so white light shines through and we track the colors that don't come through. So these are the ones that are absorbed. And if we look at the maxima of this graph, it's right here. It's right at 500 nanometers. And so this compound is absorbing light, the most light in the 500 nanometer region. It's also getting some out here around 560. And so looking at our color wheel, and this is kind of generic here, let's go look for that 500 region that it's absorbing in, and it's going to be somewhere around here. right? Um, and so we're going to look at the opposite of that on our color wheel. And so this kind of green is going to correspond to an opposite that's kind of on the red. And this picture here might not be doing it justice, that it's more of a red purple, I guess. So it's kind of in this general region here that we're seeing. And so this color is also coming from the contribution here, closer to about 550, 560, which is here, right? And so it's also absorbing light in this region. And so we're going to get a combination of, so we're absorbing this green and yellow light. And so we're going to see this violet red color to our eyes, because that's the color that remains of the white light that we're actually going to see. And so if you're a painter, this is a little bit different. So this is different than mixing colors that are pigments when we talk about the complementary colors on a color wheel for light. So we can calculate this, of course. We can calculate that crystal field splitting from the wavelength of light that we observe, that we know is being absorbed. Because, and this is going back to our conversations about the electronic structure of an atom. The energy of a photon of light is going to be equal to Planck's constant times its velocity. Well, that's going to be equal to Planck's constant times the speed of light divided by its wavelength. And so this wavelength is something that we can measure. And we're measuring the wavelength of light that's absorbed by a compound. And Planck's constant and the speed of light, these are both constant values that we can look up. And so we can, from that wavelength of light that's absorbed, calculate the energy of the photon. Well, that energy of the photon is going to correspond to, because it's just one photon of light that's coming from that that's being absorbed to make that electronic transition. That's going to be our crystal field splitting energy. So for that same titanium compound, if we just focus on the maximum wavelength, which was at 500 nanometers, and there was a shoulder further out, which influenced the color we observed. But if we start with that and we use Planck's constant and the speed of light, we can calculate that crystal field splitting energy. And so we're going to plug in our constants. Here's Planck's constant here, 6.626 times 10 to the negative 34th, and then 3 times 10 to the 8th for the speed of light. And note that's in meters per second. And our wavelength is in nanometers right here. And so we're going to need to convert that to meters using just a simple metric conversion. And plugging this all in, we're going to get an answer. We're going to get the energy of that photon that was used to absorb energy into the next energy level in the d electrons was 3.98 times 10 to the negative 37 joules. An extremely small amount of energy, but we're just talking about one photon. And we could then, scale that out to a mole of photons if we had a mole of particles. And so we can actually quantify that energy difference in those d electrons just by looking at the light that's absorbed, which is a pretty powerful thing because it gives us a lot of information about the electronic structure of that atom with those ligands. And that can help us identify what ligands are actually bonded to that atom. And also we can learn a lot about just the nature of those bonds in general. So give this problem a try, and then I'll go over the solutions in another video.